Mars is sold as the next great adventure, but there is a darker possibility people avoid. The first humans who land there may never come home, not because of one dramatic disaster, but because Mars makes return depend on too many fragile systems working for too long in a place that gives humans almost nothing for free. And once you see what it really takes to survive there, the question stops being how we get to Mars and becomes whether Mars will let us leave. If you enjoy the video, make sure to hit like and subscribe. Let's begin. The biggest mistake people make is treating Mars like a harder version of places we already know how to reach. They think of ships, remote settlements, dangerous voyages, and then a return home after the mission is done. That frame is wrong from the start. Mars is not another continent. It is not a place where the environment is difficult but still basically compatible with human life. Mars is a place where the outside can kill you all the time, with almost no margin for error, and with no real rescue path once you are there. That changes everything. The reason this matters is simple. If you use the wrong comparison, you also use the wrong expectations. On Earth, even the harshest places still give you air pressure, gravity your body knows, some way to move resources, and some way for other humans to reach you. Mars gives you almost none of that. The air is almost non-existent for human purposes. The cold is severe. The dust is dangerous to systems. The communications delay is so long that even asking Earth for help can take the better part of an hour for one question and one answer. So the first trap in the Mars story is psychological. People hear the next frontier and assume this is exploration history repeating itself. It is not. This is the first time in human history that going there and coming back are not just two parts of the same journey. They are almost two separate engineering achievements. So what does distance really do? It does more than make the trip longer. It changes the meaning of failure. Mars is on average about 140 million miles from Earth, and NASA planning has long treated a human Mars mission as something like a 3-year separation from home. That means the comforting idea of a quick abort is gone. On the Moon, you are days away from Earth. On Mars, you are months away, and sometimes much more than that depending on where the planets are in their orbits. If something serious breaks, it does not stay a short-term emergency. It becomes part of the crew's daily reality. A malfunction is not just a bad moment. It becomes something the crew has to live with while still keeping the rest of the mission alive. That one fact changes how the first crew will actually live. They will not feel like temporary visitors doing a dangerous trip and then heading home. They will feel like people already separated from Earth who are trying to keep a fragile chain of systems working long enough to maybe leave later. That is much closer to the real situation. The first Mars crew will not wake up each day with rescue behind them. They will wake up knowing that every system around them has to keep working because there is no fast way out. Then comes the next question. If the plan is a round trip, does that not solve the problem? Not really. A round trip to Mars is not the normal version of a Mars mission, it is the much harder version. That sounds obvious until you follow the logic all the way through. To bring humans home from Mars, you do not just need to land them safely, you need to send all the right hardware across interplanetary space. Land it through one of the hardest entry and descent environments in the solar system, keep it operating on the surface for months to years, and then launch a crew back out of Mars gravity to meet another spacecraft in orbit. Every one of those steps has to work, not just once, but in sequence, and after long delays. That is why one-way missions are simpler in pure engineering terms. A crew can reach Mars without proving that it can also leave Mars. The moment you add return capability, the mission gets heavier, more complex, and much more fragile. Now you need more landed mass, more power, more storage, more maintenance, more consumables, more spare parts, and more surface operations. So the first people who land on Mars will not arrive with some clean, simple ride home, waiting quietly in the background. Their survival will depend on whether an entire network of systems keeps working after touchdown for a very long time. And that leads to a harder truth. People love the idea of backup systems. On Earth, backups sound comforting because Earth has deep support behind every machine. A failed system can be replaced, a damaged component can be shipped, a team of specialists can step in. On Mars, a backup is just another system that also had to survive launch, cruise, landing, dust, cold, radiation, power stress, and human maintenance. In other words, a backup on Mars is not support from civilization. It is just more equipment that your tiny crew now has to manage. That does not remove fragility. In some cases, it increases it, because it adds more things that must be powered, inspected, repaired, and trusted. This is the part people usually skip. The real danger is not that engineers do not know what to build. The real danger is that Mars turns every requirement into a long-duration requirement. Life support is not enough. You need life support that lasts and can be repaired locally. Power is not enough. You need stable power that can support every other critical system without interruption. A habitat is not enough. You need a habitat that stays sealed, safe, and operational after months of wear. A return vehicle is not enough. You need a return vehicle whose fuel, thermal condition, electronics, and overall readiness can survive the whole surface mission. Mars keeps adding conditions. That is why the risk grows after landing, not before. So when does the real mission begin? Not at launch, not even at landing. The real mission begins the moment the crew has boots on the ground and has to keep everything alive. That is when the headlines end and the actual test starts. From that point on, every day is about preserving the possibility of leaving later. The crew has to maintain air, water, power, communications, habitat pressure, surface mobility, suit function, health, and timing. If even a few of those start slipping together, the return plan does not disappear in one dramatic moment. It slowly becomes less realistic. That is why the first humans on Mars may fully intend to come home and still never make it back. Intention is not the same thing as capability. And capability on Mars is not a ship parked and ready. Capability is a chain. It is atmosphere processing, propellant production, storage stability, reliable energy, habitat integrity, medical autonomy, crew performance, and orbital timing all holding together at once. The public story makes return sound like the final phase of the mission. In reality, return is something the crew has to keep earning every day they survive on Mars. Once you look at it that way, the honest opening to this whole story becomes very simple. The first humans on Mars will not really be visitors in the normal sense. They will arrive expecting a temporary stay, but they will be living under conditions that are much closer to settlement than visitation. They may talk like they are going back soon. They may plan like they are going back soon. But the planet does not care about that plan. Mars only cares whether the systems hold long enough for departure to remain possible. And if they do not, the first humans on Mars will face a brutal reality very quickly. They will not be settlers pretending to be explorers. They will be settlers pretending to be visitors. The first crew on Mars will not leave when they want. They will leave when the planets allow it. That is one of the hardest facts to accept because people still think of a Mars mission like a remote trip with a flexible return date. It is not. Earth and Mars line up for efficient travel only in windows that come roughly every 26 months. That means the door home is not open all the time. It opens on a schedule set by orbital mechanics, not by human need. If the crew misses that window, they are not delayed by a weekend or even by a season. They are stuck waiting for the next alignment. So every problem on Mars instantly becomes a countdown problem. Can the crew repair the damage, restore the system, recover the timeline, and still be ready before the planets move on? If the answer is no, then Mars has already decided that they stay longer. That changes the meaning of every failure. On Earth, when something breaks, you usually ask how fast it can be fixed. On Mars, you also have to ask whether it can be fixed before the geometry of the solar system closes your way home. A damaged fuel system is not just a damaged fuel system. A health problem is not just a health problem. A delayed power campaign is not just a delay. Every one of those problems now eats into a very specific launch opportunity, and when that opportunity is gone, no amount of wanting to leave can bring it back. The first humans on Mars will live under that pressure every day. They will know that physics is running the real schedule. So what happens when you need help? People assume Earth will guide them through it. But even when everything is working perfectly, Earth is still late. For a crewed Mars mission, the one-way communication delay can reach 21 to 23 minutes. That means a single question and answer can take close to an hour. By the time mission control hears your problem, the problem is already old. By the time their advice reaches you, the situation may have changed again. So you are not really having a conversation with Earth. You are sending a record of what already happened, and then waiting while reality keeps moving. That matters much more than most people realize. In low Earth orbit, you can ask for help almost in real time. On Mars, every crisis becomes local by force. If a life support system starts drifting, if a software fault appears in the return chain, if a pressure problem shows up in a tank, the people on Mars cannot wait for Earth to think out loud with them. They have to act first and get advice later. And that is a huge part of why the first crew may never come back. If the return system starts failing, they will not have live troubleshooting from thousands of experts. They will have delayed advice from a civilization that is always behind the moment. And then the situation gets worse. Because even delayed communication is still communication. Mars does not guarantee even that. There are periods called solar conjunction, when the sun sits in the way between Earth and Mars and interferes with signals. These blackouts are not rare accidents. They are built into the mission environment. They are expected. They can last for weeks. Robotic missions already have to reduce sensitive operations during conjunction because the interference can corrupt commands and data. For robots, that is a planning problem. For humans, it becomes something much more serious. Now think about what that means at the wrong time. The crew may need a specialist on Earth to review a medical issue. They may need ground teams to confirm a software patch. They may need guidance on a navigation update, a hardware anomaly, or a fault in the system meant to bring them home. And during conjunction, that support chain can be cut or degraded exactly when they need it most. So the first crew will not just be far away. At times they will be unreachable in the most literal sense that matters. Not emotionally distant. Not strategically distant. Actually unreachable. That leads to the next major misunderstanding. People hear the word abort and assume it still means what it meant in earlier human spaceflight. Something goes wrong, you stop the mission, and you go home. Mars does not work like that. NASA's own Mars abort work makes this clear. An abort in transit can still take months, not days. On the surface, abort options are limited. During descent and ascent, they are limited. In some mission architectures, a transit abort may not even be practical in the way people imagine. In later phases, an abort may only shorten the mission by weeks or months. That is a complete break from the older logic of escape systems. This point is easy to underestimate because the word abort sounds reassuring. It sounds like control. It sounds like an exit. But on Mars, abort often just means a different version of the same long problem. It does not mean instant safety. It does not mean you're suddenly out of danger. It may just mean you're now following a different path through danger for a very long time. After a certain point in the mission, the crew is no longer protected by the idea that they can simply stop and return. After a certain point, the only way out is still through the mission. That is when the emotional structure of the mission changes, even if nobody says it out loud. Somewhere after departure from Earth, one assumption quietly dies. The assumption is this: if things get bad enough, we can always come back. For Mars, that is not really true. Not in the way people think. The crew may still have a return plan, they may still have a return vehicle in the architecture, but the old emotional safety net is gone. They are now committed to timings, systems, and conditions that they cannot freely control. And that is why Mars stops feeling like a destination and starts feeling like a trap built by timing. Not because the crew is careless, not because the mission is badly designed, but because the mission only works inside narrow windows, long delays, and limited choices. If one major repair takes longer than expected, the window shrinks. If one member of the crew gets sick, the schedule shifts. If power production falls behind, propellant generation slips. And if the launch stack is not ready when the planets are ready, then the crew stays. The planets do not make exceptions for effort. This is where the public version of Mars and the real version separate completely. The public version says the first crew will go to Mars, do their mission, and then come back when the job is done. The real version is harsher. The first crew will be working inside a timetable set by celestial mechanics, with delayed communication, periodic blackouts, and very limited abort logic. They will not leave when they feel finished. They will leave only if every important part of the mission is ready at the same time the solar system allows departure. That is a much narrower path than people admit. And once you understand that, a disturbing possibility becomes very clear. The first humans on Mars do not need one giant disaster to get stuck there. They only need a return chain that is always almost ready, but not ready enough before the window closes. That is how Mars can keep people without a dramatic ending. Not with one explosion, not with one fatal mistake, just with delay, timing, and a long series of problems that never quite become impossible, but never get solved fast enough either. That is the point where the mission changes in silence. The crew may still speak in the language of return. Mission control may still speak in the language of return. The world may still expect the language of return. But underneath all of that, the truth becomes harder and harder to ignore. On Mars, home is not where you want to go. Home is where orbital mechanics still permits you to reach. The trip to Mars is not just travel time. It is the first stage of physical damage. People talk about getting to Mars like the real danger begins when the crew lands. That is wrong. The damage starts during the flight, long before Mars fills the window. On Curiosity's trip to Mars, the radiation assessment detector measured about 1.8 millisieverts per day inside the spacecraft from galactic cosmic rays. NASA's own comparison was blunt. That is like getting a whole-body CT scan once every 5 or 6 days. And that is not the surface of Mars. That is just the commute. So by the time the first humans arrive, they will already have spent months being exposed to deep space radiation that slowly changes cells, raises cancer risk, and adds long-term damage the mission cannot undo. That is one of the biggest things people fail to understand about a Mars mission. The return trip is not a safe ride waiting at the end of success. It is another pass through the same radiation environment. So even in the best case version of the story, the crew does not go through one dangerous exposure phase and then come home. They go through it on the way out, then live with the consequences on Mars, then face it again on the way back. That means the body is being taxed before the real surface mission even starts, and the price keeps building the entire time. Then there is the next hard fact. The first humans on Mars will not arrive in great shape. They will arrive weakened. In space, the human body starts adapting to weightlessness in ways that are bad for long missions. NASA says astronauts can lose roughly 1% of weight-bearing bone density per month without countermeasures. That is a serious number. On the International Space Station, crews fight this with about 1.5 hours of exercise a day, 6 to 7 days a week, using specialized equipment and constant support. Even with all of that, space still pushes the body in the wrong direction. And a Mars mission will not have the same level of resupply, the same room, or the same margin. So by the time the first crew gets to Mars, they may already be dealing with bone loss, muscle loss, reduced stamina, and cardiovascular decline. That matters because landing on Mars is not the end of the hard part. It is the moment they have to start doing dangerous work on the surface. They will have to move in suits, handle equipment, inspect systems, and respond to problems in partial gravity after months of deconditioning. A stumble on Mars is not just embarrassing. In a suit around critical hardware, far from a hospital, it can become serious very fast. So no, the first crew does not land at peak performance. They land already carrying damage, and the body does not just lose strength, it may also lose clarity in ways that are harder to predict. NASA has identified spaceflight-associated neuroocular syndrome, or SANS, as one of the major health risks relevant to Mars missions. Around 70% of astronauts on the ISS experience some swelling in the back of the eye. NASA also says the long-term outcome is still being investigated. That should get much more attention than it does. One of the major unsolved risks for deep space travel is that long periods in space can affect vision and the brain-eye system in ways we still do not fully understand. This matters because Mars is not a place where you can afford degraded performance. The first crew may need sharp vision for piloting, inspecting seals, reading instruments, spotting damage, operating rovers, doing repairs, and staying alive outside the habitat. If extended spaceflight changes vision or visual processing before the crew even lands, then the mission starts the surface phase with one of its most important human abilities already partly compromised. That is not a small medical detail. That is a direct threat to every other system the crew depends on. Then there is radiation again, because radiation does not stop being a problem after arrival. Mars surface radiation is lower than what the crew gets during cruise, but lower does not mean safe. NASA's measurements on the ground found a slowly varying daily dose of about 210 micrograys, mostly from galactic cosmic rays, and NASA has been very clear that solar particle events remain one of the biggest unknowns when trying to predict human radiation exposure on Mars. That uncertainty is dangerous because it means the crew is not just living under a steady risk. They are living under a risk that can rise sharply. A major solar event does not just threaten long-term health on paper, it can change the mission in real time. The crew may have to shelter, surface work may stop, EV may be delayed. Maintenance schedules may slip. Critical inspections may be postponed. If the mission is already running on tight timelines for power, water, hardware servicing or return preparation, then a solar event is not just a medical issue. It becomes an operational problem that spreads into everything else. Once again, the same body risk that sounds abstract from Earth becomes another reason the return chain can fall behind. And the deeper problem is this. All of these effects stack. Radiation is not the only issue. Bone loss is not the only issue. Vision changes are not the only issue. Isolation, confinement, sleep disruption, stress, closed-loop living, and the simple mental burden of knowing there is no quick way home all pile on at the same time. So when people picture the first human stepping onto Mars, they usually imagine a strong, triumphant crew starting the next phase of the mission. The more realistic picture is much harsher. They will step onto Mars after months of deep space exposure, months of physiological change, months of limited living conditions, and months of carrying growing medical risk into a place with no real hospital. That changes the whole meaning of the mission. Mars is not a clean split between outbound and inbound. It is not travel first, then the mission, then the trip home. It is one continuous medical strain from departure onward. The body takes damage during transit. It takes more strain during surface operations. It may face more radiation and more stress during return. And every issue that develops on the way out has to be carried into the next phase instead of being reset. There is no real recovery point. There is only progression. That is why the phrase "come home after the Mars mission" is misleading. By the time the first humans get there, coming home has already cost them much more of their bodies than most people admit. They will not arrive fresh. They will not arrive fully healthy. They will not arrive with all options still open. They will arrive with damage already accumulating, and with the knowledge that any new medical problem now has to be managed far from Earth, far from full care, and under conditions where every lost day affects survival and return. This is where the heroic version of the Mars story starts breaking down again. The first humans on Mars will not just be fighting the planet outside. They will also be dealing with the fact that the trip itself has already reduced their margin. Their bones may be weaker, their muscles may be weaker, their cardiovascular system may be less ready, their vision may be less reliable, their radiation exposure will already be high, and all of that will be true before the hardest part of the mission even begins. So when people ask whether the first humans on Mars will come back, the honest answer is not just about rockets and fuel. It is also about whether the crew can stay functional long enough for the return plan to remain possible. Because Mars does not receive healthy people and then test them. It starts testing them on the way there, and by the time they land, the medical gamble is already well underway. Mars has an atmosphere, but for humans that fact is almost meaningless. A lot of people hear the word atmosphere and assume Mars is at least somewhat like a cold desert on Earth. It is not. NASA measurements put the surface pressure on Mars at around 6 to 10 millibars, which is roughly 1/100th of Earth's sea level pressure. Curiosity's early readings were around 6.9 to 7.8 millibars. That is not just thin air. For a human body, it is extremely close to vacuum, so the outside of Mars is not a place where you can survive briefly with difficulty. It is a place where exposed human biology is immediately in the wrong environment. That changes how you should picture the planet. Mars is not a windy, dusty desert in the way people casually think. It is a near vacuum that still moves dust around. That sounds strange, but it matters. Because when people say things like, "We'll live under domes and just go outside in suits," they make the problem sound smaller than it is. The problem is not just that Mars has harsh weather. The problem is that the outside environment is fundamentally incompatible with human life all the time. Not during storms, not in some regions, every second of every day. So then comes the obvious question. If Mars has air, why is that still not enough? Because what little air exists is mostly useless to you. Curiosity confirmed that the Martian atmosphere is about 95% carbon dioxide. That can help if you want to make oxygen with the right machinery, but that does not mean Mars is giving you breathable air. It is not. You cannot inhale it. You cannot depend on it to protect you from decompression. You cannot treat a broken seal as something you might survive for long. Every breath the crew takes has to come from systems. Every EVA depends on systems. Every habitat pressure cycle depends on systems. Every plan to make oxidizer for a return vehicle depends on systems. Mars has air, but it is not the kind of air that lets humans belong there. This is where the public version of Mars starts breaking again. People hear that Mars has carbon dioxide and think that sounds useful. It is useful, but only after you build machines to process it, power those machines, maintain those machines, and trust those machines for years. That is the real pattern on Mars. The planet gives you almost nothing in a directly usable form. Even the things that sound promising only become useful after a lot of engineering. So the first crew will not be walking into an environment with a few natural advantages. They will be entering an environment where almost every basic need has to be manufactured. And the atmosphere problem gets worse when you connect it to water. On Earth, liquid water is normal. It sits on the surface, moves through the air, shapes weather, supports sanitation, supports farming, and supports life without humans having to constantly force it into existence. On Mars, that whole assumption is gone. NASA's MAVEN results make the point clearly. Liquid water is not stable on Mars' surface today because the atmosphere is too cold and too thin. That sounds like a science detail, but it is much bigger than that. It means Mars does not naturally support one of the main conditions that makes human life and human infrastructure possible. So usable water on Mars is not something you casually collect from a stream or a lake. It becomes hidden, buried, frozen, contaminated, or heavily processed. It becomes infrastructure. And that matters for return in a very direct way. A planet where liquid water cannot just remain on the surface is not a planet that easily supports people trying to live there, maintain equipment there, and then launch home from there. It is a planet where basic habitability has to be built almost from zero. The crew does not arrive and adapt to Mars. They arrive and begin replacing Mars with engineered conditions in small sealed volumes. That leads to the next hard fact. On Mars, a spacesuit is not just protective gear. It is a full life support system that has to keep working every minute it is being used. NASA's human risk work highlights decompression sickness, low oxygen risk, carbon dioxide management, and injury risk during EVAs. That means a Mars suit is not clothing in any normal sense. It is pressure, air handling, temperature control, power, communication, mobility, and survival packed around a human body. If it fails badly, the crew member does not have a lot of time. That is the actual margin. And this is where the return argument becomes much more serious. The first crew will not use suits for a few symbolic moonwalk-style moments, and if humans are going to survive on Mars long enough to even try to come back, they will need suits for repeated real work outside. They will need them to service power systems, inspect structures, move equipment, dig for water-bearing material, repair processing hardware, check propellant systems, and travel between assets. In other words, The possibility of going home may depend on years of outside work done through wearable life support systems operating in dust, partial gravity, cold and isolation. That is not a comforting setup. It means the return mission is only as strong as a set of pressure vessels the crew has to keep reliable for a very long time. If suit joints wear down, if seals degrade, if dust gets into critical interfaces, if carbon dioxide handling becomes less reliable, if one serious EVA injury happens at the wrong time, then the damage does not stay local. It can spread into maintenance delays, lost work hours, missed repairs, and slipping timelines for everything else. Once again, Mars does not need one giant disaster to trap the crew. It only needs the outside work to become harder, slower, or riskier than planned. And that is the point where the dream changes shape. Mars stops looking like a place you go out into and starts looking like a place you hide from continuously. The crew will not be living on Mars in the casual sense people imagine. They will be moving between controlled spaces while the outside remains hostile all the time. Habitat to rover, rover to worksite back to habitat. Suit on, seal check, pressure check, air check, every move filtered through engineering. That is not a small detail of life on Mars, that is life on Mars. Once you fully accept the atmosphere problem, a lot of the optimism around early Mars missions becomes harder to defend. Because now, the mission is not just about landing safely. It is about keeping humans alive inside artificial environments every second they are there. It is about maintaining crystal pressure, oxygen, temperature, seal integrity, and suit function with no room for laziness and very little room for error. And if your return architecture depends on months or years of successful outside operations in that environment, then leaving Mars is not just technically hard. It is dependent on a level of sustained system performance that humans have never had to prove on another world. That is why the phrase bad air is too weak by a long way. Bad air sounds inconvenient. Mars is much worse than inconvenient. Mars has almost no usable air, almost no forgiving pressure, and no outside environment where the human body can function on its own. The first crew will not step into Mars as if it is a rough but manageable place. They will survive only by carrying their own conditions with them, and by keeping those conditions intact every day. And once a mission works like that, the basic truth becomes very hard to avoid. Mars is not a place you simply visit and then leave when you are ready. It is a place where the outside keeps forcing you back into machines, back into maintenance, back into caution, and back into delay. And if every path home depends on years of work in that kind of environment, then Mars is not just difficult to leave. By physics alone, it is built to keep the first crew there longer than planned. Getting humans onto Mars is not a solved problem. It's not even close. People talk about a human landing on Mars as if it is just the next upgrade after rovers. Bigger mission, bigger rocket, same basic idea. That is not true. NASA's 2024 human landing white paper notes that only 12 out of 19 attempted robotic Mars landings had succeeded. That record is for robots. Robots do not need breathable air. They do not need a pressurized cabin. They do not need food, water, medical care, radiation protection, or a vehicle waiting to take them back off the planet. So before you even get into the details, the first reality is already brutal. Humans do not yet have a routine, proven, human-scale Mars landing system. The first people who try this will not be using mature infrastructure. They will be testing the most important hardware of the whole mission in one of the hardest environments we know. And Mars is hard in a very specific way. The atmosphere is bad for landing in both directions at once. NASA describes it as thin, but still thick enough to create serious heating. That is what makes Mars so difficult. When you hit the atmosphere, you're coming in at extreme speed, so you still have to survive intense heating on the way down. But after that, the air is too thin to slow you down the way Earth can. So Mars gives you enough atmosphere to burn you, but not enough atmosphere to stop you properly. That is why entry, descent, and landing on Mars has always been one of the nastiest parts of any mission there. You cannot ignore the air, and you also cannot trust the air to save you. This is where people usually make the next mistake. They look at successful landings like Curiosity, or Perseverance and assume human landings are just a scaled-up version of that. They are not. NASA says all flown Mars entry, descent and landing systems so far have landed masses between about 0.3 and 1 metric ton. Human-class landers will need landed masses above 20 metric tons. That is not a small increase. That is more than 20 times heavier than the systems that have actually worked. So everything people point to as proof that we know how to land on Mars is operating in the wrong class. It is like saying you know how to land a fully loaded airliner because you once landed a motorcycle. That gap matters because landing physics does not scale up cleanly. A robotic lander can accept risks and limits that a human lander cannot. A rover can land hard enough to stress hardware but still complete a mission. A human landing cannot. A rover can survive with no cabin, no crew volume, no life support reserves, no safe internal environment after touchdown. Humans cannot. A robotic mission can afford a much smaller target in terms of immediate survival needs. A human mission cannot. The first crew will need a landing system that works at a mass scale Mars missions have not yet demonstrated in real life. That is the real gap, not a step. A gap. Then there is the issue of where you land. For robots, landing near the target is great. For humans, landing near the target may not be good enough. NASA points out that traditional parachutes are inherently unsteerable, and wind drift can add a kilometre or more of landing error. A kilometre on Mars is not a minor inconvenience. That can be the difference between reaching your habitat and not reaching it. It can be the difference between being close to power system, supplies and ascent hardware, or being far enough away that safe movement becomes a mission problem by itself. And Mars does not make that easier by being flat and predictable. Orbital imaging can identify very small features, down to around 25 centimetres in the best cases, but NASA still uses examples like a 1-metre boulder sitting within 8 metres of Viking 1's landing site. That tells you something important. Even when you know a lot about the terrain, you do not know everything. Mars can still hide the exact kind of hazard that matters at the exact scale that matters. A robot can sometimes tolerate that. A human landing system carrying the whole future of the crew has far less room to accept that kind of uncertainty. This becomes even more serious when you remember that human missions are not landing into an empty story. They are landing into a whole surface architecture. The crew may need to come down close to habitats, power systems, stored supplies, rovers, fuel production hardware, and eventually the vehicle that gets them back off the planet. So, somewhere nearby stops being acceptable. On Mars, a little off-target can mean too far to live, too far to move critical cargo, too far to connect with the systems that keep the crew alive, too far to make the mission work the way it was planned. And then Mars adds one more trap. The same engines that help save you on landing can also damage the place you need to survive. NASA's entry, descent and landing work warns about plume surface interaction. When large retropropulsive landers fire their engines near the ground, they can erode the soil and blast debris outward. That debris can strike the vehicle. It can strike nearby hardware. It can damage surfaces, lines, connectors, panels, and anything else close enough to get hit. Phoenix exposed subsurface ice with its landing engines, which was exciting science for a robotic mission. For a human mission, that same effect is a warning. Powerful engines do not just place you on Mars, they disturb Mars violently right under you. That means even touchdown becomes a trade. You need powerful landing systems because the atmosphere is too thin to do enough braking on its own. But the more powerful those landing systems are, the more they can disturb the landing site and threaten nearby assets. So the very rockets that get humans safely onto Mars can also sandblast the infrastructure they need for life support and return. That is not a side issue. That is part of the landing problem itself. On Mars, even success can damage your future if the landing is not managed perfectly. This is why the first human landing on Mars is so much more than a dramatic arrival. It is a compression point where several unsolved problems all meet at once. You have extreme entry speeds, serious heating, weak atmospheric braking, very large payload mass, tight landing accuracy requirements, uncertain terrain, and engine effects that can damage the site on arrival. And all of that has to work not just well enough to touch down, but well enough to preserve the systems that keep the crew alive after touchdown. That is a much harsher standard than most people realize. So when people say the first humans will land on Mars and begin the mission, the real answer is more uncomfortable. The landing is part of the mission to stay alive. It is part of the mission to maybe leave later. If the landing is too hard, too far off target, too damaging, or too messy, the crew may survive the arrival and still lose the margin they needed for everything after it. That is what makes Mars different. It does not separate arrival from survival cleanly. It forces both to happen at once. And that is why this part of the story matters so much. Before the first humans ever worry about leaving Mars, they first have to survive getting down to it with a system no one has yet proven at the scale humans need. That should completely change how you think about the mission. Because on Mars, the first step is not planting a boot. The first step is surviving a landing that is still, even now, barely proven for machines. And if touching down is this uncertain, then the next question gets even worse. Once you land, what exactly are you trusting to keep you alive every hour after that? The most important structure on Mars is not the rocket. It is the place that keeps the crew from dying while they wait to use the rocket. A lot of people still picture a Mars base like a remote house, a station, or a shelter. That is too simple. A Mars habitat is not just where the crew lives. It is the system that has to replace what Earth normally does for free. It has to provide pressure, breathable air, water recycling, food storage, temperature control, waste handling, radiation protection where possible, sleep conditions, hygiene, and emergency refuge. On Earth, all of that sits inside a much bigger support system called a planet. On Mars, the habitat has to become that support system in miniature, without ever really shutting down. That is why NASA treats hostile enclosed environments as a major hazard. The habitat is not a background detail, it is the thing holding the line between life and the outside, and that matters directly for the question of coming home. People like to focus on the return vehicle, but the return mission sits inside the habitat mission. If the base becomes unstable, then the launch vehicle does not matter anymore. It does not matter if the crew technically has a way off Mars later, if they cannot keep themselves alive long enough to reach that point. So before you ask whether they can leave Mars, you have to ask whether they can keep their artificial Earth running every hour until departure. And this gets more serious when you look at the details. Even basic human needs turn into engineering requirements. On Earth, sleep sounds normal and private hygiene sounds ordinary. On Mars, both become technical problems that have to be solved properly, or the mission starts slipping. NASA's habitability standards explicitly talk about controlling vibration, lighting, noise, and temperature for sleep, and also making room for privacy, hygiene, and normal personal functioning. That sounds small until you understand what it means. It means the crew cannot just survive in a sealed can and be expected to perform well for years. They need an environment that protects cognition, mood, attention, memory, and cooperation. This is easy to underestimate because none of it sounds dramatic, but this is exactly how long missions fail. Not always from one giant break, sometimes from constant low-level stress that slowly makes people less sharp, less patient, less rested, and less reliable. A habitat that is too loud, too bright at the wrong times, too cramped, too exposed, or too difficult to live in does not just make the crew uncomfortable. It makes them worse at decisions, worse at repairs, worse at teamwork, and worse at noticing small problems before they become dangerous. On Mars, that is not a quality of life issue. That is a mission survival issue. Then the biology of a closed environment starts creating its own problems. A Mars habitat is not just a sealed living space. It is a sealed ecosystem with humans inside it for a very long time. NASA's risk work includes altered immune response, changing interactions between humans and microorganisms, nutrition problems, and worsening behavioral health as major concerns for Mars missions. That means the crew is not only managing machines, They are also managing what happens when a few human bodies, their microbes, their waste, their food systems, and their environment are locked together for months and then years. Dormant viruses can reactivate. Skin and gut microbiomes can shift. Small nutrition gaps can become performance problems. Stress can turn into illness, and illness can turn into lost labour. This is where the habitat stops looking like a structure and starts looking like the main character of the mission. If the habitat slips, everything slips with it. If food quality drops, crew health drops. If hygiene systems become harder to maintain, disease risk changes. If air handling becomes less reliable, concentration and sleep can suffer before a true emergency even starts. If microbial control gets worse, surfaces, water loops, filters, and crew health all become connected problems. And unlike the ISS, Mars missions will not have regular resupply to smooth over mistakes, spoilage, shortages, or degraded equipment. The crew will be living with what they brought, what they can repair, and what they can stretch. Food alone shows how serious this really is. Most people still think of space food as packaged meals and ration planning. But for Mars, that logic starts breaking. NASA's Mars food work makes clear that a sustainable food system for Mars has to be nutritious, safe, reliable, and efficient in resource use. And in the long run, it has to provide the full nutritional value the crew needs without depending on high-mass strategies that only make sense for shorter missions. That is not the language of a short visit. That is the language of building a support chain that starts behaving like the first version of an off-Earth biosphere system. And once you are building systems like that, the meaning of the mission changes. You're not just packing enough supplies for a trip. You're building infrastructure that has to keep producing value after landing. Food production, food preservation, water recovery, waste recycling, air handling, and health maintenance all start tying together. That is exactly the kind of architecture that makes a mission drift toward permanence, even if permanence was never the original public goal. Because once the crew has invested months or years in keeping that life support chain stable, leaving is no longer the only rational choice. In some situations, preserving the outpost may start looking safer than risking the chain that gets them off Mars. That is the part many Mars stories avoid. A functioning Mars base is not just a shelter. It becomes something the crew will fight to protect because every day of survival depends on it. And it never really stops being vulnerable. On Earth, buildings usually fail gradually and within a much larger environment that still supports human life around them. On Mars, the habitat is always under pressure to keep Earth-like conditions inside a place that would kill the crew very quickly if the shell, seals, pumps, scrubbers, valves, or power supply fail in the wrong way. That means every leak matters, every strange reading matters, every maintenance task matters. And because the first crew will be small, every failure costs more than just hardware time. It costs human time. One person investigates the fault. Another person covers routine work. Another person loses sleep. Another delay hits inspections, surface tasks, or return preparation. A bad week inside the habitat can spread into the entire mission. That is how Mars turns repair into destiny. The crew may want to focus on science, exploration, and getting ready to go home. But if the base keeps demanding attention, then survival work starts taking priority over everything else. That is why the habitat sits underneath the whole Mars story. The first crew will not simply be living in a base while doing a Mars mission. Keeping the base alive will be the Mars mission for a huge part of the time. The return vehicle depends on it. Crew health depends on it. Sleep depends on it. Food and water depend on it. Morale depends on it. Decision-making depends on it. If the habitat becomes unstable, the rest of the mission does not continue normally. It starts collapsing inward. So when the return window finally comes, the crew may not feel like explorers deciding whether it is time to leave. They may feel like exhausted technicians who spent months or years barely holding a fragile artificial environment together. And that changes the whole idea of choice. Because if going home means taking on another huge risk while the only stable thing they have is the habitat they already fought to preserve, then leave now stops sounding automatic. On Mars, home is not where you were born. Home is the machine that is still working. The system that decides whether the first humans survive on Mars is not the rocket. It is power. People like to talk about fuel, landing, habitats and food as separate problems. On Mars, they are not separate. Power sits under all of them. If electricity drops, air processing drops with it. Water extraction drops with it. Heating drops with it. Communications, medical equipment, food systems, drilling, nerding, pumps, valves, storage control and fuel production all start falling together. NASA's own Moon to Mars planning says the first explorers will need energy to live, work and ascend back to orbit. That tells you the real structure of the mission. Power is not one important subsystem among many. Power is the base layer of the whole mission. If it slips, nothing else stays healthy for long. That is why Mars power has to be understood in survival terms, not in engineering terms alone. On Earth, a power problem can be serious, but usually there are alternatives. You can call the grid, you can repair the line, you can move people, you can prioritize one building and borrow support from a larger network. On Mars, there is no larger network. Power is air because your life support systems need it. Power is water because extraction and processing need it. Power is heat because the habitat and equipment need protection from extreme cold. Power is time because every delay in a low power condition pushes every other task later. A weak power system does not just make the mission less efficient, it starts closing the path home. Then there is the part Mars adds that makes this even worse. Dust storms are not rare surprises there. They are part of the planet. NASA says Mars gets moderately large dust storms every year. These can cover areas the size of continents and last for weeks. And more rarely, about once every 3 Mars years, which is around 5.5 Earth years, those storms can grow until they wrap around the planet. That matters because people often think the main danger is wind force, like a hurricane on Earth. But Mars is not dangerous that way. The thin atmosphere means the wind is less mechanically destructive than movies make it look. The real threat is operational. Dust blocks sunlight. Dust reduces visibility. Dust coats hardware. Dust changes thermal behavior. Dust adds abrasion. Dust narrows margins. That is the part that matters for a human mission. Mars does not need to blow your habitat over to ruin your schedule. It only has to dim the systems you are counting on. If the crew is depending on solar arrays, then a storm is not just bad weather. It is a direct hit to survival and planning. It can reduce output for days or weeks. It can leave dust on panels after the storm has passed. It can make outside work harder at the same time the crew most needs to protect and restore their power supply. That is how Mars turns a weather event into an infrastructure event. And this is not theoretical. We have already seen dust end missions. Opportunity did not die because it ran out of science to do. It died after a severe Mars-wide dust storm in 2018. Its final communication came on June 10th. After that, NASA sent more than 1,000 recovery commands, but the rover never came back. That was a robot built for Mars, on a mission where survival demands were far lower than anything a human base would face. Then in 2022, another large dust storm, nearly twice the size of the United States, forced InSight into safe mode and delayed Ingenuity flights, because the dust reduced sunlight reaching the solar arrays. Again, those were robots. No crew, no heated living space, no pressure shell to protect, no medical systems, no oxygen plant, no return chain waiting on stable energy. So take that same environment and scale it up to human stakes. A human outpost cannot go into a simplified safe mode and patiently wait without consequences. People still need air circulation, thermal control, water processing, communications, lighting, refrigeration for some supplies, habitat systems, and ideally ongoing work on the equipment that gets them home. A severe drop in available energy does not just pause exploration. It starts a chain of priorities. First you protect life support, then you protect heat, then you protect the habitat itself. Everything else gets pushed down the list. And once that happens, the first thing that starts looking optional is often the thing the public cares about most, the return timetable. This is why solar power by itself turns Mars into a waiting game. Solar can absolutely play a role, but on Mars it is tied to too many variables. It depends on how much dust is in the atmosphere. It depends on the season. It depends on where the storm tracks are. It depends on how much dust sticks to the panels. It depends on how much storage you brought. It depends on how well you can clean or maintain the system. And for a human mission, good enough most of the time is not enough. The system has to keep working through bad periods, not just through average periods. It has to hold habitat safety. It has to hold key equipment temperatures. It has to hold margins for processing, storage, and return preparation even when conditions get worse than normal. That is why serious Mars mission concepts so often lean toward fission support. Not because nuclear power sounds bold or futuristic, but because Mars punishes dependence on sunlight. A human mission cannot gamble its future on whether the sky stays clear enough. It needs a power source that does not care about dust opacity the same way solar does. It needs something steady enough to support survival first and industry second. Because make no mistake, return from Mars is partly an industrial problem. If the crew has to make propellant, run processing hardware, manage storage, and keep systems stable for long periods, then unstable power is not a small inconvenience. It is a direct threat to departure. And this is where the real logic turns cruel. If power starts falling short, the crew does not get to protect everything. They have to choose. They save life support before they save fuel production. They save heat before they save long-range plans. They save the habitat before they save the launch schedule. That is not weakness. That is rational survival. But it is also how Mars quietly converts a return mission into a long stay. Not with one dramatic failure, with a series of correct decisions made under energy pressure. First, the crew delays one process, then another. Then they pause a non-essential operation. Then they reduce outside work. Then a return-related target slips. Then the window starts looking harder to hit. That is how it happens. The first humans on Mars will not stand in the habitat and announce that they are becoming permanent residents. It will be much quieter than that. They will look at the numbers, they will look at the output curve, they will look at the storage margins, the dust load, the temperature requirements, and the list of things that must stay alive. And at some point the math will force the truth on them. If there is not enough power for everything, then there is only enough power for survival. And once that happens, coming back stops being the active plan. It becomes the thing they hope they can restart later. That is why power is the system beneath all systems. It decides how much air you can process, how much water you can recover, how much food support you can sustain, how much equipment you can run, how much fuel you can make, and how much time you still have before one delay becomes another missed chance. On Mars, low power is not just a technical state. It is a state inside the mission. It forces priorities. It forces sacrifice. And the dream that usually gets sacrificed first is not survival on Mars. It is departure from Mars. That is how the first humans may end up staying longer than planned. Not because they stop wanting Earth, not because they forget home, but because Mars only has to weaken the power margin at the wrong time, and the rest of the mission begins choosing for them. Mars has water. That does not mean the first humans can actually use it when they need it. This is one of the most misleading facts in the whole Mars story. People hear that Mars has ice and immediately relax. They think that solves one of the biggest survival problems. It does not. NASA's newer ice maps show that in some regions, likely water ice sits within about 3 feet or 1 meter of the surface. Phoenix directly confirmed near-surface water ice back in 2008. So the science is not the problem. We know water is there. The problem is everything that comes after that. Buried ice is not drinking water. It is not clean tank water. It is not ready to use life support. It is frozen material buried under dirt in a hostile environment that has to be found, dug up, processed, purified, stored, and protected. That turns water into a full industrial chain. And that is where the easy version of the Mars story falls apart again. On Earth, when people think about water, they think about access. On Mars, access is only the first step. The crew will need machines that can excavate or heat the ground, collect the water, separate it from soil, move it through systems, check contamination, and keep all of that running in cold, dust, and low gravity. So the real issue is not whether Mars has water. The real issue is whether the first crew can turn buried frozen material into reliable civilization-grade water day after day without breaking the rest of the mission. That is a very different question. Then comes another problem that gets less attention than it should. The best place to land is not always the best place to mine. A human landing site has a long list of needs. It should have smoother terrain. It should be safe enough for a very large lander. It should have workable latitude, useful communications geometry, manageable dust and lighting conditions, and access to whatever science or mission goals matter. But the best water ice does not automatically line up with the safest landing site. NASA's Mars planning has kept returning to this same tension. You want near-surface ice, but you also want a place where humans can actually survive touchdown. That matters because the first crew may end up landing somewhere chosen mainly because it is survivable for landing, not because it is ideal for resource extraction. And that changes the whole workload. If the crew is not sitting right on top of easy-to-reach ice, every litre of water becomes more expensive in time, energy, and labour. The public story makes Mars water sound like a resource waiting to be used. The real story is closer to this. The crew may spend huge amounts of effort just reaching, extracting, and moving the material they need to stay alive. And every extra step adds more exposure, more wear on equipment, and more chances for delay. Then the situation gets worse, because even after you get the water out, it is still not ready. Mars water is not clean. NASA's 2024 work on detoxifying Mars water says it clearly. Subsurface Martian ice contains toxic perchlorates. These chemicals are hazardous to human health and corrosive to equipment, even at low concentrations. That means water on Mars is not just hidden, it is chemically hostile. So the crew does not simply find ice, melt it and use it. They have to remove dangerous contaminants before that water can go into propellant system, food production, or the human body. This is a major point because it changes the meaning of success. Even if the first crew locates the right ice, reaches it, excavates it, and extracts water from it, they are still not finished. They still need purification. They still need monitoring. They still need systems that can keep doing that job without poisoning the crew, damaging hardware, or contaminating the wider life support chain. That makes water on Mars not just a resource problem, but a chemistry problem, a reliability problem, and a maintenance problem all at once. And the demand for water rises the moment humans arrive. This is another place where people think too narrowly. Water is not just for drinking. On Mars, water becomes hygiene. It becomes food production. It becomes oxygen loop chemistry. It becomes thermal management. It becomes cleaning. It may affect suit operations. And most importantly, it can become part of the fuel chain that gets the crew home. NASA's own Mars planning keeps linking water to both survival and ascent capability. So if water extraction or purification falls behind, the crew does not just face discomfort. The whole return architecture starts taking damage. That is the real danger. The same water the crew needs to stay healthy may also be tied to the oxygen or methane production needed for launch. So now, a shortfall in water is not one problem. It becomes several problems at once. Less water for people, less margin for hygiene, less confidence in food systems, less support for chemical processes, less support for propellant production. That is how Mars turns one missing resource into a mission-wide threat. And just like power, the mission does not fail all at once. It starts rationing. First one process slows down, then another slips. Then one return target gets pushed, then another. And eventually the plan to leave starts depending on a water chain that never caught up. This is why Mars quietly turns explorers into miners. The public story sells images of footprints, flags, and surface exploration. But the engineering reality is much more repetitive and much more demanding. The first crew will spend huge amounts of time doing resource work. Digging, heating, extracting, filtering, detoxifying, storing, inspecting, repairing, then doing it again. Because on Mars, water is not something you discover once. It is something you have to keep producing in a usable form over and over again, and that changes the emotional shape of the mission. The first humans will not spend most of their time doing the kind of exploration people usually imagine. They will spend much of it trying to turn buried, dirty, chemically dangerous ice into safe water for a functioning outpost. That is not a side task. That is central to whether they live there and whether they ever leave there. If the water chain underperforms for too long, the crew does not need one dramatic collapse to get stuck. They only need the extraction rate to stay lower than planned and the maintenance burden to stay higher than planned. That is enough. Because once water starts lagging, the mission gets forced into the same brutal logic we have already seen in other systems. Survival first, return later. Humans first, fuel later. Habitat first, departure later. And if that pattern keeps repeating, the mission slowly stops behaving like a round trip. It starts behaving like the first stage of permanent habitation, even if nobody ever officially says that was the goal. That is the hardest truth in this section. Mars has water, but Mars does not hand water to you. It makes you work for every part of it. It makes you excavate it, clean it, protect it, and build a whole support chain around it. And if the first crew spends too much time and power doing that just to stay alive, then they may find themselves in the exact position this whole story keeps pointing toward. Not dead, not defeated, just still there, because the resource system they needed for survival never became reliable enough to support departure. A rocket on Mars is not a ticket home. That is the biggest mistake people make when they think about return. They picture a crew landing on Mars with a vehicle that will eventually take them back. But on Mars, the vehicle is only one part of the problem. The real problem is fuel. More specifically, the real problem is whether the first crew can build and keep running a fuel economy on another planet. NASA has treated oxygen production from the Martian atmosphere as one of the key enabling technologies for human Mars missions for a long time. And if you add water extraction from the ground, then in theory you can produce both oxygen and methane for a return vehicle. That sounds clean and simple when you say it fast. In reality, that means the first humans only come home if they also create the first working propellant industry off Earth. That changes the whole meaning of the mission. The first crew does not return because they brought a spacecraft. They return only if they brought a factory, powered a factory, maintained a factory, verified the output of that factory, and then trusted their lives to what it produced. That is not a side project happening next to the main mission. That is the main mission. Because if the fuel production chain fails, then the return vehicle is just a piece of hardware sitting on Mars with nowhere to go. This is exactly why MOXIE matters so much, and also why MOXIE should make people much more cautious. MOXIE was a brilliant success. It proved that oxygen can be pulled from the Martian atmosphere. On Perseverance, it generated a total of 122 grams of oxygen, and at peak performance it made about 12 grams per hour at high purity. That is a real breakthrough. It is proof that the chemistry works on Mars, but it is also proof of how far the mission still has to go. Human return does not need proof that oxygen can exist. Human return needs industrial amounts of oxygen made reliably, at scale, with stable purity over long periods, with storage and timing that fit a launch plan. That is the part the public usually misses. A technology demonstration and a return system are not the same thing. MOXIE made Mars feel more possible, but it also showed the size of the gap between possible in principle and ready to send people home. The first crew does not need a laboratory success. They need production at a mission scale. They need days, weeks, and months of dependable output. They need confidence that the system will not drift, contaminate, clog, freeze, lose power, or start underperforming halfway through the campaign. Because once the crew starts depending on locally made propellant, there is no small failure. Every shortfall moves directly into the return question. NASA's own studies make that gap very clear. One ISRU case study found that a surface system of about 1.7 metric tons could remove the need to carry around 30 metric tons of ascent propellant from Earth. That sounds like an enormous benefit, and it is. But look at what it also means. It means the mission is betting heavily on a relatively compact processing system, doing a huge amount of work correctly on Mars. Another NASA study on human ascent describes a Mars ascent vehicle that relies on oxygen gathered on the Martian surface, with oxygen production taking up to 1 year. 1 year? That means your ride home may depend on a factory operating on another planet for about a year before you can trust that the vehicle is ready. That is not a backup plan. That is a second mission running underneath the first one. The public version of the mission says this: humans land on Mars, do the work, then launch home. The real version is more like this: humans land on Mars while another long-duration mission is already in progress, and that second mission is the industrial campaign that may or may not make departure possible. If the factory underperforms, the crew waits. If storage becomes uncertain, the crew waits. If power margins tighten, the crew waits. If the chemistry output is not good enough, the crew waits. The first return mission is not just about surviving on Mars, it is about surviving long enough for Mars to manufacture the right to leave. And even that still understates the dependence. The return rocket is not really sitting there alive and ready in the way people imagine. NASA ascent studies assume the vehicle gets connected to surface power within 24 hours of landing. That is because power is needed for oxygen production and also for preventing propellant boil-off. So the ascent vehicle is not parked like a normal vehicle waiting in a garage. It is an active system tied into the whole base. Its future depends on surface energy, thermal control, communications, storage conditions, monitoring, maintenance, and crew time. If those systems weaken, then the rocket does not simply wait a little longer. It starts drifting away from readiness. That is a very uncomfortable reality. The crew may look at the ascent vehicle every day and still not truly have a ride home. Because until the fuel is made, stored, protected, and verified, that vehicle is only a promise. And promises can decay. Tanks can lose margin. Lines can become suspect. Valves can become unreliable. Thermal conditions can drift. Sensors can mislead. Power interruptions can create knock-on effects. On Mars, the rocket home is not separate from the colony around it. It is metabolically dependent on the colony. If the base gets weaker, the rocket gets weaker. This is why the whole return idea becomes much harsher when you look at it seriously. The first humans may land on Mars in a spacecraft, but they do not leave Mars with a spacecraft alone. They leave only if they can first establish the seed of a working settlement. In a system sense, they need power generation, they need atmospheric processing, they need water extraction, they need chemical production, they need storage, they need maintenance, they need verification, they need repair capacity, and they need all of that to stay stable long enough for launch confidence to become real. So when people say the first Mars mission will be a round trip, that statement hides the hardest part. The actual return system is not just the ascent vehicle. It is the whole industrial ecosystem around the ascent vehicle. It is everything that keeps the propellant chain alive and trustworthy. And that means the first humans on Mars may find themselves in a very strange position. They may survive the landing, survive the habitat, survive the dust, survive the medical strain, and still not be ready to leave because the industrial system underneath the return plan never reached full confidence. That is the hardest truth in this entire part of the story. The first return mission may not really be a mission at all in the simple sense. It may be the outcome of whether the first Martian industrial ecosystem works. If the ecosystem works, the crew may go home. If it works late, they stay longer. If it works partially, they keep waiting and testing. If it never reaches the level of trust a crew descent needs, then the first humans stay on Mars no matter what the original plan said. So no, the first crew does not come home because they landed a rocket. They come home only if they successfully build the first off-world fuel industry and keep it alive in one of the most hostile environments humans have ever entered. And if that sounds less like a visit and more like the beginning of a settlement, that is because it is. Mars does not give you medical care. It gives you medical responsibility. That is the real situation the moment the crew leaves Earth. A lot of people talk about the first Mars mission as if medicine is just another support system running in the background. It is not. On Mars, there is no hospital down the road, no evacuation flight, no specialist arriving tomorrow, and no quick resupply if something important is missing. NASA's own hazard framework makes the point clearly. Distance and the communication delay make medical care, fresh supplies, and real-time Earth support much harder. So the first crew will have to handle serious illness, injury, unclear symptoms, and long recovery periods with only what they brought, what they can power, what they can diagnose, and what they themselves know how to do. That means the medical system on Mars is not really a medical system in the Earth sense. It is a limited room, limited equipment, limited diagnostics, and a very small group of people trying to solve problems under pressure. That matters because when people say the first crew will come home later, they skip over the part where the crew first has to survive all the way to that later point without the kind of medical support humans normally depend on. That is not a side challenge. That is one of the core tests of the entire mission. The first Mars crew is not just proving that humans can live far away. They are proving that humans can stay medically independent far away. And that turns even small medical problems into mission problems. On Earth, a painful but non-fatal condition can still be manageable because the system around you is huge. You can get scans, pain control, specialist care, monitoring, and backup if something gets worse. On Mars, the same condition can shake the whole mission. NASA's work on kidney stones shows why. Long-duration spaceflight and reduced gravity can increase the risk because bone loss can release more calcium into the body. An untreated kidney stone can cause severe pain, nausea, and in some cases would normally lead to evacuation. NASA has even noted that kidney stones are the second most likely reason for emergency medical evacuation from the ISS. But on Mars, that familiar escape route is gone. So now picture what that actually means in mission terms. One crew member develops severe pain, they may not be able to work, they may not be able to sleep. They may need constant monitoring, extra hydration, medication, and help moving around. Another crew member becomes the caregiver. Someone else has to take over lost tasks. The rest of the crew is now operating more tired, more distracted, and with less flexibility. Nothing about that requires a fatal injury. Nothing about that requires disaster. It only requires one painful medical event happening at the wrong time. That is how Mars takes a survivable health problem and turns it into pressure on the whole return architecture. Then there is the fact that space changes the immune system too. NASA has warned that radiation, microgravity, poor sleep and other space stressors can alter immune function. Dormant viruses can reactivate. That includes viruses behind cold sores and shingles. On Earth, that might sound manageable. On Mars, it is not just about one person feeling unwell. It is about what illness does inside a closed habitat with a tiny crew and no real backup. Every illness affects workload. Every illness affects mood. Every illness affects sleep. Every illness affects the small human margin keeping the whole outpost running. And that is the part people miss. The crew is not only fighting the external environment, their own bodies may become less stable partners over time. A body that is tired, stressed, under radiation exposure and living in a closed system for months is not behaving under normal conditions. So even minor illness matters more. Skin problems matter more. Infections matter more. Recovery takes on more importance. A few lost days on Earth are frustrating. A few lost days on Mars can ripple into delayed maintenance, missed inspections, slower resource work, and more strain on the rest of the team. The medical issue does not stay in the medical room, it spreads into everything else. And Earth cannot really guide the crew through this in real time. That is another major break from how people imagine the mission. On Mars, even the best doctor on Earth becomes a delayed consultant. Telemedicine stops being live care and turns into time-shifted advice. A procedure does not happen with someone walking you through it second by second, and it happens because the crew has already trained for it, already rehearsed it, and can now carry it out while waiting for later input from Earth. That means the first Mars crew needs far more medical autonomy than any earlier space mission. Not just for routine issues, but for rare and serious ones too. This is where medicine stops being a separate category of risk and becomes part of the return problem directly. Every day lost to illness is not just a bad day for the patient. It is a day not spent fixing equipment, producing resources, checking systems, or keeping the departure chain on track. Every delayed recovery means more burden on the rest of the crew. Every uncertain diagnosis means more hesitation about how much risk the mission can take next. On Mars, medical uncertainty competes directly with return readiness. The crew does not have spare people standing by. It does not have a deep bench. It has a handful of humans, and every one of them matters. That is why one crew member going down changes the whole mission math. A Mars surface mission is a tiny labour ecosystem. If one person becomes non-functional, another becomes a caregiver, another takes extra EVA duties, another has to handle more maintenance, another loses sleep covering tasks or worrying about the patient. Very quickly, the mission starts running hotter and thinner. The crew may still be surviving, but the margin starts disappearing. And the return schedule is built on margin. It is built on enough healthy people doing enough work on time for long enough to keep every system ready. This is what makes the idea that the first humans may never come back stronger than it first sounds. You do not need a giant accident. You do not need a habitat rupture. You do not need one huge medical catastrophe. All you need is a string of serious but survivable setbacks, pain that lasts too long, fatigue that spreads, recovery that takes longer than expected, an infection that interrupts work, a vision issue, a mobility problem, a condition that is not fatal but keeps one person from doing their full share. Mars does not have to kill the crew to keep them there. It only has to keep them busy, tired and behind. And that is the hardest part of this whole section. On Earth, medicine is part of the system that gives people margin. On Mars, medicine is about protecting margin that is already very small. The first crew will not have the luxury of treating health as a private issue. On Mars, every health problem becomes operational. Every symptom matters more. Every medication matters more. Every missed hour of sleep matters more. The crew will not just be asking, can this person survive? They will also be asking, can this crew still keep the mission alive if one person cannot do their part? Once you see that clearly, the story changes again. The first Mars mission is not simply a test of whether humans can reach another planet. It is a test of whether a very small group can remain medically functional long enough, with enough independence to preserve the chance of leaving. And that is a much harder standard than most people realise. Because on Mars, you do not get a hospital when something goes wrong. You get the consequences. A Mars mission can survive a lot of hardware trouble for a while. It cannot survive a broken crew for long. That is why NASA is already treating the psychology of Mars as a serious engineering problem, not a soft issue to think about later. Chapea is built around year-long Mars surface simulations with 4 crew members living in about 1,700 square feet. Hera goes even smaller, around 650 square feet, and focuses on isolation, confinement, and communication delay. That tells you the real concern. Before NASA can trust humans on Mars, it has to know whether a tiny group can stay stable, competent, and cooperative under long stress, delayed communication, and limited resources. The first crew on Mars will not just be doing science and maintenance, they will be carrying one of the hardest social experiments in human history. And that matters because Mars does not give people emotional release. On Earth, stress has exits. You can leave a room, you can take a walk, you can call someone and hear an answer right away. You can disappear for a while and cool down. On Mars, almost none of that exists in a normal form. The crew will hear the same voices every day. They will see the same walls every day. They will follow many of the same routines every day. At first, that sounds manageable. Over time, it stops being ordinary and starts becoming corrosive. NASA's behavioral risk work treats isolation, psychiatric strain, and teamwork problems as real mission hazards for exactly this reason. Confinement does not just make people bored, it slowly changes how they react to each other, how they interpret tone, how they carry stress, and how long they can stay patient. That is where monotony becomes dangerous, not because it is dramatic, but because it is constant. A small irritation that would normally disappear can stay alive for weeks. A disagreement that would normally cool down can keep getting touched by the same people in the same environment. A joke can become annoying, a habit can become intolerable, a silence can start to feel hostile. On Mars, there is no easy reset. There is no weekend away, no outside world to mix the social atmosphere, no fast emotional grounding from family or mission control. Even a walk outside is work, risk, and equipment. So the first crew will not just be dealing with the planet. They will be dealing with the same human tensions under pressure for months and then years. And if trust starts thinning, every other system starts feeling weaker too. Then there is the next shift, and it is even more important. Delay changes command itself. In low Earth orbit, Earth can still guide, advise, and intervene quickly enough to shape the moment. On Mars, that model breaks. By the time Earth hears a question and responds, the situation has already moved. That means the crew has to carry more autonomy, more distributed skill, and more authority inside the habitat. From a mission design point of view, that makes sense. From a human point of view, it is heavy. Because more autonomy does not just mean more freedom, it means more burden. It means the crew knows that the hardest calls belong to them. That changes the emotional weight of every decision. Risk tolerance changes, leadership changes, responsibility changes. If there is a repair choice, they have to own it. If there is a medical judgment, they have to own it. If the return systems look uncertain, they have to live with that uncertainty before Earth can say much that changes anything. The first Mars crew will not just be isolated from Earth by distance. They will be isolated into adulthood in a much harsher sense. They will be making decisions that feel final in ways astronauts rarely experience now. There will be no strong illusion that mission control is carrying the real load behind the scenes. The people on Mars will know the load is on them. That sounds empowering until you ask what happens when the crew does not agree. NASA already treats inadequate teamwork as a direct mission risk, and on Mars that makes perfect sense. A Mars base is too small and too fragile to absorb social fracture. One serious conflict does not stay personal for long. It spills into sleep, maintenance, EVA planning, medical trust, communication style, and confidence in big decisions. If two people stop trusting each other, that is not just a bad atmosphere. It can affect whether a repair gets double-checked properly. It can affect whether a safety concern gets voiced clearly. It can affect whether a sick crew member believes the others will support the right call. And the hardest disagreements will not be the obvious ones. They will be the high-stakes technical decisions that arrive after months of stress. Is the ascent system really ready? Is this fault acceptable or not? Do we push one more EVA cycle now or wait? Do we spend power on this process or preserve margin somewhere else? Do we trust the numbers enough to leave? Those are not abstract leadership exercises. Those are decisions where social trust and technical judgment mix together. A Mars crew may discover that the hardest thing to keep stable is not the habitat shell. It is shared confidence. Once consensus starts weakening, every major decision becomes slower, more emotional, and less reliable. And that is exactly why isolation on Mars is not just about morale. It changes how the crew thinks. It changes how they define acceptable risk. It changes what feels urgent. It changes who they feel responsible to. At first, Earth will still feel central. The launch dates, mission plans, public promises, and return schedules written on Earth will still feel like the main structure of the story. But the longer the crew survives on Mars, the more the logic of Mars starts taking over. Immediate habitat needs feel more real than distant goals. A repair needed today feels more real than a return timeline written months earlier. The people beside you feel more real than the audience back on Earth. That is a huge shift, and it is not irrational. It is exactly what humans do in real environments. They orient toward the conditions that actually keep them alive. So if the crew has spent months holding the base together, protecting the power system, managing medical strain, solving water and air problems, and keeping each other functional, their loyalty starts leaning toward the local reality that made survival possible. That means Earth's priorities do not automatically keep winning. The crew may start judging success less by whether they launch on schedule, and more by whether the outpost stays stable. That is not failure, it is adaptation. But it can pull directly against the idea of coming home as soon as possible. This is the part most Mars stories do not want to touch, because it sounds too strange at first. The first humans may never come back, not only because of physics, hardware, or fuel, they may never come back because place changes people. The longer they live under Martian conditions, the more their mission culture may drift away from the simple Earth story of out and back exploration. They may start thinking like the custodians of an outpost, not the passengers of a return mission. They may start protecting continuity over closure. And by the time return is technically possible, they may see leaving as the bigger risk to everything they built. That would be an extremely human outcome, not a cinematic disaster, not one giant failure. A slow change in priorities under pressure. First survive, then stabilize, then preserve, then hesitate, then reassess whether launch is worth the risk. And if that process repeats enough times, Mars does not need to trap the crew by force. It only needs to keep teaching them the same lesson. The outpost you are standing in matters more right now than the planet you came from. So when people talk about the first Mars mission, they usually act as if the main test is whether the hardware can endure. That is not enough. The real test is whether the crew can endure together without drifting into conflict, fatigue, mistrust, or a new local logic that slowly rewrites the mission from the inside. Because on Mars, isolation does not just make you lonely. It changes how you decide, who you answer to, and what going home even means. Mars is not stable ground with a bad sky above it. The ground itself is part of the danger. A lot of people think the surface of Mars is just cold, quiet, and dead. That is not true. NASA's InSight mission detected more than 1,313 Marsquakes. One of them, in May 2022, was estimated at magnitude 5, the largest quake ever observed on another planet. That matters because a long-term human base depends on assumptions about the ground under it. The crew will be counting on stable footing for habitats, buried cables, pipes, landing pads, storage systems, and anything else that has to sit on or under the surface for years. Mars does not need constant violent quakes to create trouble. It only needs enough activity to remind you that the surface is not passive. That changes how you should think about a Mars outpost. It is not just a sealed structure sitting on quiet terrain. It is a fragile system resting on a planet that still moves. Even moderate ground motion can matter if you are relying on buried hardware, carefully aligned equipment, and structures that have to hold pressure in a hostile environment. On Earth, engineering already has to respect seismic risk. On Mars, you have to do that with less repair margin, less construction margin, less manpower, and no outside rescue. So even if Marsquakes are not catastrophic most of the time, they still add another layer of uncertainty to every long-duration plan. And Mars does not just move from within, it still gets hit from above. NASA's later InSight work linked meteoroid impacts to seismic signals that travel deep into the Martian interior. That means Mars is still being struck, still being shaken, and still being physically reworked. So the environment the first crew faces is not only thin air, radiation, cold, and dust. It is also a surface that is still part of an active planetary story. That broadens the risk in a very important way. A Mars base is not just defending itself from a static hostile background. It is sitting on a world that still changes under force. That matters because a human outpost is a concentration of vulnerability. Habitats, power systems, vehicles, storage units, landing zones, and life support connections are all fixed assets. They are all things the crew depends on being where they should be and working the way they should work. If the environment includes impacts, shaking, settling, or surface shifts, then the crew is not just protecting against obvious threats from above and outside, they are also trusting the ground below to stay cooperative enough. On Mars, even the soil under your base is part of the risk picture. Then there is dust again, but here it is important to be exact. Mars dust is not the disaster movie version people know. NASA has been clear that Martian dust storms probably would not rip apart a human habitat the way fiction often shows. Winds in major storms can reach around 60 miles per hour, but the atmosphere is so thin that the force is much lower than an Earth hurricane. That sounds like good news until you understand what the real problem is. Dust on Mars is dangerous not because it hits hard once, but because it keeps wearing systems down. That is the more serious version of the problem. Dust coats solar panels, dust gets into joints and moving parts, dust reduces visibility, dust changes how surfaces heat up and cool down. Dust adds friction, contamination, and maintenance demands. It does not have to destroy a base in one violent event. It just has to reduce performance a little, then a little more, then a little more, until the crew is spending more and more of its time keeping systems alive. That is how a base turns into a maintenance colony. Not through one dramatic failure, but through constant small losses caused by the environment. And those small losses matter, because Mars keeps stacking them.
The same dust that reduces power can also make outside work harder. The same dust that lowers visibility can slow down rover movement and inspections.
The same dust that gets into seals and mechanisms can shorten the life of the very equipment the crew needs for water, power and fuel production. Once again, Mars does not need one giant disaster to stop a return mission. It only needs enough system degradation at the wrong times. Then there is the terrain itself. People often treat terrain as a landing problem, but it does not stop being dangerous after touchdown. The rocks, slopes, loose regolith, and uneven surfaces that make landing difficult will still be there for every EVA, every rover trip, every drilling operation, and every cargo movement. And those tasks will be done by humans who have already spent months in deep space and are now living in partial gravity with changed bodies. NASA's own fitness risk work warns that deconditioning makes tripping and falling more likely during gravity transitions. That is a serious issue on Mars because a fall is not just a minor accident. A fall on Mars can damage a suit. It can injure a joint. It can fracture bone. It can force the end of an EVA. It can damage equipment being carried. It can consume medical supplies and crew time. It can put another person into a caregiver role. In other words, one bad step can spread through the mission much faster than people expect. The surface does not have to be extreme to be dangerous. It just has to be unforgiving. And Mars is unforgiving. A loose patch of soil, a hidden rock, a bad slope, or a moment of fatigue can suddenly become a chain of delays the crew never fully recovers from. That is why the ground itself becomes part of the one-way argument. If Mars were only far away, then maybe the problem would mostly be transport. If it were only cold, maybe insulation would be enough. If it were only dusty, maybe cleaning systems would handle it. But Mars does not give you one clean challenge. It gives you active geology, impact risk, surface wear, dust cycles, rough terrain, and human deconditioning all at once. And that combination matters more than any one headline danger. Because missions usually do not fail only from one giant blow, they also fail from too many medium-sized problems arriving over and over again. One extra repair, one delayed traverse, one damaged seal, one crew member who falls and needs recovery, one buried line that needs checking after ground movement, one storm that forces a pause, one more week lost, then another. That is exactly the kind of pressure that can keep a crew on Mars longer than planned without ever producing the single dramatic disaster people expect. So when people ask whether the first humans will come back, they should not only look up at the rockets or out at the distance, they should also look down. Because the ground under a Mars base is not neutral, it is part of the mission load. And once you add an active surface to every other problem Mars already has, the same pattern keeps getting stronger. The first crew does not need to be defeated in one moment. They only need to be slowed, worn down and delayed by enough real but survivable problems that not yet keeps winning over launch now. And when a mission lives on not yet for long enough, Mars stops being a place you're stuck on for a while. It starts becoming the place you still live. The vehicle that is supposed to bring the first humans home from Mars is not really a lifeboat while they are living there. It is a machine under care. That is the first thing people need to understand. NASA's own human Mars ascent studies do not treat the ascent vehicle like something you land, park, and forget until departure day. They treat it more like a long-term patient. The plan assumes oxygen is generated on Mars, that the vehicle gets connected to surface power within 24 hours, and that the whole system may spend up to a year producing and preserving the propellant needed for launch. That means the ship home is not home yet. It is another surface system that has to survive Mars for a very long time. That changes the way you should think about the whole return idea. A lot of people picture the crew landing on Mars with their ride home basically waiting in the background. But until the fuel is made, until the tanks are stable, until the power stays reliable, until the thermal conditions stay controlled, and until the system passes every check that matters, that vehicle is just another vulnerable piece of hardware sitting in a dangerous place. It can lose margin, it can drift out of spec, it can become less trustworthy over time. On Mars, a vehicle does not stay ready just because it exists. It stays ready only if a whole support network keeps it ready. And this is where the situation gets even stranger. In some NASA ascent concepts, the crew is not expected to spend much time directly inside or around the Mars ascent vehicle during the surface mission. In fact, one concept minimizes crew access so heavily that serious access starts only the day before launch, with some preparation beginning the day before that. That is efficient from an engineering point of view because it reduces contamination risk and unnecessary complexity. But it is also deeply unsettling. It means the people whose lives depend on that vehicle may spend months living next to it without really using it, without really inhabiting it, and without having the kind of familiarity people normally want with their only escape route. Think about what that means psychologically. The crew is supposed to trust a machine they mostly monitor from the outside. They are supposed to believe that the sensors are telling the truth, that the maintenance logic is sound, that the analysis is good, and that the systems they have not lived inside for months will suddenly be exactly what they need on launch day. That is a very thin kind of trust. It is not the trust you get from daily use. It is the trust you get from data, procedures, and hope. And on Mars, hope is never enough by itself. Then look at how boarding that vehicle is supposed to happen. NASA's Mars ascent studies describe the crew reaching it by pressurized rover and tunnel, so Martian soil does not contaminate the ascent cabin. Even that one detail says a lot. It tells you that after all the preparation, after all the system care, after all the waiting, the final act of going home still has to happen inside a very tight procedure designed to keep one more form of risk under control. The crew is not casually walking up a ladder and climbing in. They are moving through a controlled chain, where contamination itself is a serious concern because even small environmental interference can matter at the worst possible moment. And the suit details make the fragility even clearer. Some NASA concepts assume the crew remains in suits, with visors up through ascent and docking except for brief hygiene breaks. That is not a normal, comfortable ride home. That is a sign of how little margin the system expects to have. If the crew is staying suited through ascent and docking in part because of concern over cabin leak risk, then the message is very clear. Even after years of planning and a long surface campaign, departure from Mars still starts in conditions that look more like a controlled emergency than like routine transportation. That should completely change how people think about the phrase return vehicle. A real lifeboat is something you can get into fast when everything else is going wrong. The Mars ascent vehicle is almost the opposite. It depends on everything else having gone right for a very long time. It depends on power. It depends on storage. It depends on the propellant campaign. It depends on the habitat and surface system staying stable enough to support its care. It depends on the crew staying healthy enough to use it. Until the engines actually fire, it is not a guaranteed way out. It is a long-duration promise that still has to be redeemed. And even if ascent goes perfectly, the crew is still not home. That is another public misunderstanding. Launching from Mars is not the same thing as returning to Earth. In NASA's human ascent concepts, the Mars ascent vehicle reaches orbit and then has to rendezvous with an Earth return vehicle already waiting there. So the trip home is not one vehicle doing one job, it is a relay race. First surface survival, then propellant production, then ascent, then orbital insertion, then rendezvous, then docking, then crew transfer, then the actual interplanetary return. Every one of those steps has to happen correctly. If one fails, the crew is not back. The crew is just in a different kind of danger. That matters because the public story compresses all of that into one sentence. They launch from Mars and come home. But the real chain is much longer and much more fragile. If there is a guidance issue during ascent, the rendezvous may fail. If there is a docking problem, the return chain may stop in orbit. If a system in the waiting return vehicle has degraded, then reaching orbit is not enough. If a crew member is too sick to suit up properly, the whole launch sequence may break before it starts. So the first humans will not have one return vehicle in the simple sense. They will have a return chain, and that chain is only as strong as its weakest link. And chains do not usually fail in one dramatic instant. They fray. That is the real danger here. A delayed oxygen campaign, a small contamination problem in a line, a storage issue that looks manageable at first, a power anomaly that forces new priorities, a guidance concern that needs more verification, a docking interface problem that appears late, a crew member who is technically alive and conscious, but not really fit for the demands of launch day. None of those has to be cinematic. None of those has to explode. They only have to reduce confidence enough that launch becomes harder to justify on schedule. That is the killer logic of this whole section. Mars does not need to destroy the return chain. It only needs to keep it almost ready. Almost enough propellant. Almost enough certainty. Almost enough crew health. Almost enough system confidence. Almost enough margin. And almost is not launch. On Mars, almost can keep you there for months. Sometimes for another full planetary window, sometimes for much longer. So when people picture the first crew looking out at their ship home, the harsher truth is this. They may be looking at a machine that cannot yet save them, may never fully save them, and may remain dependent on the health of the entire outpost right up to the moment of ignition. That is not a lifeboat. That is a fragile final link in a long chain of dependencies. And that is why the first humans may never come back even after building so much of the path home. Because on Mars, you do not need the chain to snap. You only need it to keep fraying faster than the crew can finish it. The deeper you look at a Mars mission, the less it looks like a trip and the more it looks like a commitment. And one of the biggest reasons is mass. Not emotion, not ambition. Mass. NASA's own round-trip mass studies use what they call gear ratios, meaning how much total launched mass you need in order to move useful payload from Earth to Mars and then bring it back. And the numbers are ugly. In one example, an 1,100-day round-trip mission has a full mission gear ratio of about 10.6. A shorter 850-day mission pushes that to roughly 34.4. That means if you want a faster round trip, every kilogram starts dragging an enormous mass penalty behind it. So the harder you push for a quick return, the more expensive every part of that return becomes. That point changes the whole story. People often assume a shorter mission sounds safer because it gets the crew home earlier. But Mars does not reward that instinct. In many cases, it punishes it. A shorter mission can mean a much harsher mass penalty, and that means more launch burden, more system stress, and less flexibility. The rocket equation does not care about the story humans want to tell, it only cares how much stuff you're trying to move, how fast and how far. And for Mars, the answer is brutal. Fast round trips are not just harder, they become absurdly expensive in mass terms. So once you understand that, the mission starts changing shape. If you already paid the mass, energy, money and risk to land people on Mars, along with their habitats, power systems, water processors, vehicles, medical supplies and industrial equipment, then using that foothold longer starts to make more sense than rushing to undo it. That is the part people do not like to say out loud. Because once the first crew is there and still alive, the logic of the mission starts pushing away from leave as soon as possible and toward get more value out of what you already built. And that is where the settlement question starts appearing, even if nobody officially uses that word. This is not just ideology, it is mission logic. The economics of return are so harsh that once the crew has survived landing and stabilised the outpost, staying longer can start looking more rational than trying to force a fast departure. If the base is working, if the power is holding, if the water systems are improving, if local production is growing, then the idea of tearing yourself away from that foothold can look less smart than strengthening it. That is how Mars changes the meaning of success. Survival does not naturally point back to Earth. In many cases, it starts pointing forward into continuity, and some people answer that by saying resupply solves the problem. Just keep sending more equipment, more spare parts, more food, more support. But resupply does not actually remove the pressure, it deepens it. Every resupply mission still has to survive the same brutal chain. Launch from Earth, interplanetary transfer, entry, descent, landing, surface integration, and long-term maintenance. Every extra cargo load is not just help, it is also more mass to move, more risk to absorb, more hardware to connect, and more systems to keep alive after arrival. Mars does not become low risk because you promise more shipments. It becomes more complex. That is why Mars mission design keeps drifting toward local production. Water extraction, oxygen manufacture, maybe methane production, maybe food growth, maybe spare part fabrication. Those are not optional bonuses for a mature colony decades later. They start becoming central very early, because imported support stays expensive and fragile. But here is the uncomfortable part. The systems that make return possible are often the same systems that make staying more likely. The better you get at extracting water, making oxygen, growing food, and repairing hardware locally, the less the mission looks like a visit. It starts looking like the first stage of permanence. This is where the public image of Mars completely splits from the engineering reality. The public imagines flags, footprints, and a dramatic return. The actual architecture demands infrastructure. Once you stack the real mass categories together, the illusion disappears. Habitat mass, ascent mass, in situ resource utilization mass, power mass, mobility mass, medical mass, surface science mass, storage mass, redundancy mass, thermal control mass. Suddenly this is not Apollo with a longer commute. It is the first fragile industrial node on another world. And industrial nodes do not exist for symbolic reasons. They exist because the math says they have to keep operating. That matters because infrastructure changes the mission emotionally and practically. Once the crew depends on an industrial base to survive, and once the return plan also depends on that same industrial base, the smartest short-term move is not always departure. Sometimes it is extension. Sometimes it is another cycle of production, another season of stabilization, another effort to improve margins, another delay to increase confidence. And that is exactly how a Mars mission can slide from temporary presence into long-term presence, without any official moment where someone says, "We have decided to stay." The decision can happen much more quietly than that. It can happen in budget logic, in risk reviews, in launch readiness discussions, in the fact that the outpost already exists and the return path still looks weak. Because once you have paid so much to build a functioning foothold on Mars, abandoning that foothold quickly can start looking less reasonable than protecting it. The mass already spent begins shaping the future. Sunk cost becomes architecture. Architecture becomes policy. Policy becomes delay. And delay on Mars is never neutral. That is why the idea that the first humans may never come back is stronger than it sounds. The more serious the mission becomes, the more it stops behaving like a heroic out-and-back story. It starts behaving like the founding phase of a long-duration off-world presence. Not because people become less brave, not because they stop loving Earth, but because the mass economics make quick closure look wasteful and unstable. If the crew is alive and the outpost is functioning, stay and build can start looking like the rational next move, even if come home was always the public promise. And that is where mass becomes something bigger than engineering. It starts rewriting the culture around the mission. The old exploration myth says brave people go out, survive the danger, and come back with stories. Mars pushes against that at the level of physics. Because for Mars, the more successful the mission is, the more expensive it becomes to treat that success as temporary. Once people are there, once systems are working, once local industry begins, continuation starts looking more efficient than reversal. That is the final pressure in this whole section. Mars does not just challenge the crew with danger, it challenges Earth with logic. It asks a simple and brutal question. If you've already paid so much to create a living foothold on another planet, why would you be in a hurry to shut that foothold down just to preserve an old story about return? And the more honest the answer becomes, the more uncomfortable the mission gets. Because by then, physics is no longer just shaping rockets, it is shaping the meaning of exploration itself. The old story says humans leave, discover, and return. Mars may be the place where that story breaks. Not because return is impossible in theory, but because once survival, infrastructure, and mass economics are all taken seriously, the smartest continuation of the mission may stop including the trip back. So what do all these problems add up to when you stop looking at them one by one? They add up to a mission that is built to stay longer than planned. That is the pattern. Radiation starts damaging the crew before Mars even arrives in the window. The atmosphere is almost no atmosphere. Landing humans at the right mass is still not an operational routine. Water has to be dug up, processed, and detoxified. Power supports every single survival function underneath the mission. The fuel for leaving has to be made on Mars over long periods. Medical care becomes local and limited. Communication is delayed and sometimes cut off. And all of it rests on a very small crew whose judgment, trust, and mental stability matter just as much as tanks, valves, and software. None of those facts by itself proves that nobody comes back. That is important to say clearly. Any one of them alone can still fit inside a hard but survivable mission. The problem is the stack. The first crew will not face one big challenge at a time in clean sequence. They will face all of them as overlapping pressures that keep eating the same limited margin. The margin in power, the margin in health, the margin in time, the margin in trust, the margin in spare parts, the margin in launch readiness. That is why the default condition of the first crew is not a clean round trip. The default condition is prolonged residence while they try to keep the possibility of departure alive. And here is the real twist. Mars does not have to beat the crew in one dramatic moment. It does not need one explosion, one fatal mistake, or one headline failure. It only needs to keep making one answer sound more reasonable than the other. Not yet to launch, not yet to risk the ascent system, not yet to divert power from survival to propellant production, not yet to send a weak crew member through a dangerous sequence, not yet to leave the base that took so much effort to stabilize, not yet to trust the numbers, not yet to close the hatch and commit. That is the kind of trap Mars sets. Not a trap made of panic, but a trap made of caution. The crew may do everything right. They may make responsible decisions, careful decisions, even smart decisions. And those smart decisions may keep pushing departure further away. First one delay makes sense, then another. Then the next launch window looks too risky. Then another cycle of staying seems more defensible than leaving. That is how the first humans on Mars may never experience one famous disaster and still never return. They may simply live inside a long series of rational delays until delay becomes the mission. And so then what does the first footprint on Mars actually mean? Most people think it means victory, proof that interplanetary travel works, proof that humans reached another world and extended the map. But that footprint may mean something much more serious than that. It may be the first moment a human being steps onto another planet and quietly crosses out an old assumption. The assumption that every human life off Earth still ends by coming back to Earth. That assumption has always been there in the background of exploration. Mars may be where it stops being true. That is why this story is bigger than rockets, habitats, or engineering charts. It is about identity. The first Mars crew will not just be testing machines. They will be testing whether people can remain psychologically centered on Earth once biology, distance, infrastructure, and daily survival start pulling them somewhere else. If your air is made locally, your water is extracted locally, your food system is partly local, your power priorities are local, your danger is local, and your crew loyalty is local, then what exactly still makes Earth the automatic center of the mission besides memory and intention? That is the point where the old frontier story starts breaking apart. For a long time, the story has been simple. Humans leave, discover, and return. That is the shape people expect. That is the shape history taught them to expect. But Mars is not built for that shape. Mars teaches something harsher. It teaches that on some worlds, arriving is easier than leaving. It teaches that survival is a bigger achievement than discovery. It teaches that mission accomplished may not be the moment the crew launches home. It may be the moment the crew realizes they can keep living there at all. And once you accept that, the meaning of exploration changes. The word still sounds temporary. It still sounds like movement out and then movement back. But at Mars distance, with Mars conditions, exploration starts looking a lot more like migration. Not because anyone planned a permanent colony in the emotional sense on day one, not because the crew stopped loving Earth, but because the physics, the logistics, and the system requirements keep pushing in the same direction. Build the base, protect the base, feed the base, power the base, repair the base, delay departure, extend the mission, strengthen the outpost, repeat. At some point that is no longer a visit in any honest sense. And that is why the first humans on Mars may become the first Martians long before anyone uses that word out loud. Not through ceremony, not through some grand declaration, through function, through habit, through survival, through the fact that the center of their life has moved. Their days are organized by Martian light, Martian risk, Martian maintenance, Martian weather, Martian resource work, Martian decisions. The place that defines what matters hour to hour is no longer Earth. It is Mars. Once that happens, return is not just a technical question anymore. It becomes a question of what kind of people they have become by staying alive there. And this is the final hard truth. The first humans on Mars may leave Earth fully expecting to come home. They may mean it. They may plan for it in complete good faith. But expectation is not outcome. Mars does not care what the crew meant to do. Mars only cares what the systems allow, what the bodies can tolerate, what the timings permit, and what the local reality keeps forcing them to protect first. So no, the first humans on Mars may not be the heroic returnees in the version of the story people like to tell now. They may be something much stranger and much more important. The first people in history to leave Earth expecting a round trip, survive long enough to build the beginning of another human world, and then realize too late that under the combined pressure of radiation, dust, fuel production, orbital timing, biology, and time itself, Mars was never really preparing to send them back. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. Like the video, and subscribe to the channel for more such amazing videos.